we ended up talking about, first of all, I'm going to answer any questions. Do you guys have any questions from anything as far as how the course is going? Is anybody here for the first time that wasn't here on Wednesday? Anybody here? Say yes down below. Anybody who wasn't here last time? Okay. Let's see. So, anybody have any questions? Any questions about anything? About the course, about tutoring, about the quizzes? Okay. Yeah, the quizzes / homework, which are the same thing. All right. It's all going to be counted towards extra credit in terms of points. And the extra credit, again, it's only a minimal amount of extra credit, up to 3 percentage points on your exam, on exam 1. That's what we're working towards now. And the percentage that you actually end up getting of those 3 percentage points will be based on the percentage that you get on the quizzes or the homework. All right? Very good. So, go ahead and put yourselves in a thumbs up mode if you're ready to talk today. But if the baby's sleeping and you can't wake him up, then put a thumbs down mode. If I see a thumbs up, that means I'll be interested. I'll include you in asking questions. Otherwise, I'll skip by you. Okay, so we were talking about scuba diving, right? We were talking about scuba diving and why it's important to come up slow from the bottom of the ocean. Camille, can you rehash that for us? Tell us, what was the reason we wanted to make sure we came up slow from the bottom of the ocean when we're scuba diving?
Because of the nitrogen that is used in the oxygen, and it could go to our brain.
Okay, it's not just the nitrogen, it's the oxygen, it's anything that's in that gas that you're breathing. But what is it? What's going on there? Describe a little bit about why it's dangerous.
Well, it doesn't like we have a certain amount of oxygen in things that we have, like the oxygen we breathe is like put through our lungs and everything, and it's filtered. And when you're breathing through there, you have to like it's through a different type of oxygen that's in an air tank, so that it would mess up and it causes hallucinations.
Okay, let's look at this example again. So here's a container, just some sort of a vessel, right? And in it I have some water, all right? I have some water in this vessel. There are gas molecules floating above, not just in the vessel, but everywhere, right? Because that's what air is. Air is an ocean of molecules of nitrogen, oxygen, carbon dioxide, right? Mostly nitrogen, 80% nitrogen, about 20% oxygen, less than 1% carbon dioxide. If these molecules of air, nitrogen, oxygen, whatever that gas is, when they collide with the water, some of them will actually dissolve into the water. And then you'll have not bubbles, but dissolved gases. You won't be able to see them, right? When they come out, if they condense and they are no longer dissolved, then yes, you'll be able to see them. They'll make little tiny bubbles and they'll float to the top. But gas will actually dissolve into a liquid. If I trap a certain amount of gas with some sort of a plunger, right, and I push down hard on this, I can force more molecules of gas to dissolve in the water. By pushing down, I could force more molecules of gas to dissolve in the water. Another thing I could do is think of a different kind of container here. I mean, it's the same kind of container, has water in it, but this time I have a lid on it. I have a sealed lid, but I have a valve. And what I'm going to do in this valve is I'm going to increase the number of gas molecules that are in here by hooking it up to some, machine, and it's going to pump an air compressor. It's going to pump gas into here. So when I increase the number of gas molecules, then what that does is that increases the pressure. And if there's more gas molecules here, there's more that can be dissolved. So I can increase it by pushing them down in, which is basically decreasing the region where the molecules are, and so it's increasing the number of gas molecules. Or I can put more of them into here like this, and that will also increase the amount of gas that will be dissolved in the liquid below. Okay? So both ways I'm increasing what we call the pressure, right? And when your lungs, so here are your lungs, ta-da, right? There's your lungs, right? Your lungs are exposed to the pressure of the gas, right? And your lungs breathe it in, and then they try to breathe out the carbon dioxide, right? Well, if you go deep underwater, the pressure of that gas increases. And so more of the gas will dissolve into the tissue and the blood, right? The blood is where the lungs are for allowing the gas to filtrate into the blood and get delivered to the rest of your body. If you're doing this at low depths, very deep, under high pressures, there will be more oxygen or nitrogen dissolved into your lungs. And then if you come up very fast, and not just your lungs, but your body and your blood and everywhere that the blood is circulated. But then if you rise to the surface very quickly, then that lowers the pressure, and the gas that's dissolved in the actual lungs and in the blood and in the tissue will come out and form little pockets, bubbles, just like you've seen bubbles on the bottom of a pan when you pour water in or something like that, or when you begin to boil something, you see tiny little bubbles that appear. And when those bubbles appear in your tissue or in your blood, that causes problems, right? That'll begin to destroy tissue, could kill specific organs, right? So that's why we get what we call the bends if you're not careful about allowing gas to exchange in and out of your lungs appropriately before you rise up. Now, as I mentioned before the end of class last time, we are at the bottom of an ocean of air. And I really like this quote. We live submerged at the bottom of an ocean of air. Right? We don't know it. We don't realize it because that's just the way we've grown up, right? But remember last time we drew this ocean. This is an actual ocean of water. And here's a person. And if you go down here, the pressure is really high because there's so much water pushing down on you. But here, there is also pressure pushing down on you because you're at the bottom of this ocean of air. All right? So this gas contributes a pressure to you. That pressure changes as you climb mountains or are at different elevations in airplanes, right? The pressure depends on where you're at relative to what we would call zero pressure or space, right? Where there's no atoms of gas, therefore no molecules of gas, therefore there's no pressure. So this pressure, just like in the balloon, right? The balloon is being held out because the molecules of gas are speeding around, banging into the sides of the wall, right? And causing this balloon to have the shape that it does. That same pressure is what's pushing around every surface of anything that's submerged in the bottom of this atmosphere. Okay, so what we're going to go through now is a series of what we call proportionality relationships, proportional relationships. Things that are proportional to each other. It means that, for example, pressure and the amount of gas, right? So if I had a container, here's another container, and let's say this is no water in it, just has a little spigot to fill up with gas, right? And if I push gas into this container, I'm pushing more and more molecules into a fixed space. And what do you think, Sarah? As I put more and more molecules into this fixed space, how is that going to change the pressure on the walls on the inside of that space, of that container?
The pressure will increase.
The pressure will increase. That's right. The more gas molecules there are, the more pressure there's going to be. Okay? We can say then that the amount of gas in the container is proportional to the pressure of the gas in the container. So N, let's say N represents the number of moles, N for number of moles of gas in a container is proportional to the pressure on the container. If you put more moles of gas in the container, the pressure goes up, right? I have another container here, drawing another picture of another container, right? This one only has very few moles of gas compared to this top one. Which one has a higher pressure, Alyssa? Which one has a higher pressure?
The top container has a higher pressure?
That's right, more moles of gas, okay? We call these proportional to each other because if you increase the moles of gas, you increase the pressure on the container. Now, I didn't say that this container was larger or smaller, right? We have to assume that we're talking about the same size because obviously, if I take this container and all of a sudden change its volume, so like if I can make it shrink down, but I have the same number of moles of gas inside, right? Then that will change the pressure, right? Same number of moles of gas, smaller volume, it'll change the pressure. Okay, so we're going to talk about how some relationships are proportional. You increase the moles of gas, you increase the pressure. On this one here, we see that you decrease the volume, but what has it done to the pressure, Alyssa? Or no, sorry, it's Preston's turn, right? Or did Alyssa, did you answer already? I think you answered, right?
Oh, I've gone. Yes, sir.
Okay, Preston, what happens to the pressure here if I take my volume and decrease it?
It'll increase the pressure?
That's right. Same number of moles of gas, but I've decreased the volume, the pressure increases, okay? So you would say then that volume and pressure, as the volume goes up, pressure actually does what? Volume, if you go back the other way, volume goes up, the resulting pressure goes down, right? So N, the number of moles of gas, and pressure are directly proportional, whereas the number of volume, or the volume of a container relative to its pressure is inversely proportional, or inversely proportional. Yes, inversely is what we call it, proportional, indirectly. Okay?
I have a question.
Yeah, go ahead.
So as the volume goes up, the pressure goes down?
All right. Yes. So make sure we're understanding what you just said. Let me draw another picture so make sure we're understanding well. Here's a container. It has in it 1, 2, 3, 4, 5, we'll say moles of gas. Okay? That each dot represents a mole of gas for whatever. Now, some magical way, I can expand the volume of that container. How many moles of gas do I have in it now, Camille?
A lot more.
Well, no, I've just expanded the container itself.
Oh, so it's going to be the same amount of gas, 75.
Right. Now, pressure is related to how many molecules there are to collide with the edges. So which one is going to have higher pressure? The left one or the right one?
The left one?
The left one is going to have the higher pressure. That's right. So we see that the volume here increased, right? But we need our pressure to go down. The pressure decreases. So what we see is that there's this inversely proportional relationship. As you increase the volume of a condition, its pressure will go down. Okay? So I find it easy to draw little pictures like that. And again, we have to recognize here that there were some things that were held constant. One thing that was held constant was the number of moles of gas, right? if you were to increase the pressure, increase the volume, but you also increase the moles of gas, then the pressure might increase depending on how many moles of gas you increase it, right? So and we'll talk about lots of different scenarios like that. To start off with, we want to recognize that some things are directly proportional, the number of moles of gas to the pressure. Some things are inversely proportional, the volume to pressure. Okay, let's look at another one here. Well, this one here is our volume and our pressure. And we see that pressure is, and we don't say equal to, right? We don't want to use an equal sign when we say 1 over volume. So I could have done I did like this here where I said volume is indirectly proportional to pressure. You can also do it like this, pressure is indirectly proportional to volume. But you don't want to use an equal sign. And the reason you don't want to use an equal sign is because pressure, what are some units for pressure? Anybody know? Let's see, David, what are some examples of units for pressure? Oh, David's not ready to answer the question. Aisha, what's some units for pressure?
Torr,
Atmospheres, millimeters of
ATM.
mercury. Very good, very good. We got a handful of different units. But let's talk about torr, whatever it is. Aisha, what are some examples of units for volume?
Liters, milliliters.
Yeah, liters, milliliters. So these are not equal, right? We can't say that the pressure equals this relationship because we don't have the same units, right? Just like you can't say the number of moles and the pressure in a container will be directly proportional, but N will be in units of moles and this will be in units of torr or atmospheres or whatever. So they're not the same units, right? However, there will be a direct proportionality. So as you see here, if I have a condition, P1, pressure initial condition, compared to volume initial condition, so let's draw our conditions again. Little container, 5 moles of gas, right? Little container, 5 moles of gas. This will be equal to a new scenario where I've changed the volume, right? 1, 2, 3, 4, 5, and I get a new pressure. All right? So as long as I know what the volume is here, I can identify what the pressure, the new pressure will be. So my initial conditions, my final conditions, you could think of it that way, right? So, for example, let's see, Precious, if you want to pay close attention to help us answer this one. If I have a pressure, let's say, of 2 atmospheres inside this container, and the volume of the container here is 100 milliliters, okay? And the new volume here is 2,000 milliliters. Can you tell me, Precious, what the new pressure is? What's P2? What's the new pressure going to be there, Precious? You there, Precious?
Yeah, hold on.
Okay. It looks like she's trying to...
Is it 40?
40. So you took the 2, you put it here, right? Oh, sorry, no, it's not 2. 2's down. Yeah, that's right. That's right. That was right. 2 for our pressure, right? And what did you use for the volume down here?
100.
100. And then the second pressure is what we were trying to solve. And we had a final volume of 2,000. So 2,000 times 2, 4,000, equals 100 times x. All right, so that's where she got 40 from. And what are the units for that 40?
Atmospheric.
That's right, atmospheres. That's our pressure. Okay, so again, we didn't have the ability to know exactly what the relationship was for this statement, pressure is equal to 1 over volume. However, if I have 3 of the 4 necessary relationships here, right, then I can see that I can identify the 4th, right? Here, let's see if we can watch this video real quick. So these are balloons inside a container. And as we take the container, and we're not putting more air into the balloons, but we're removing gas from the container itself. Now the gas can't get out of the balloons, and so the balloons are increasing in size. All right? Did you see that, Landon? What's happening to the pressure inside the balloons, Landon? What's happening to the pressure inside the balloons?
The pressure's increasing.
Okay.
When the balloons are expanding.
All right. So the pressure inside is becoming higher because there's no more pressure on the outside, but the balloons are expanding, aren't they? If the balloons can expand, then actually the pressure probably isn't increasing, right? It might be increasing a little bit, but, and as we bring the pressure inside the bell back down, then they go back down to size. All right, very good.
Could I see that practice problem again?
The practice problem? Mm-hmm.
The one we did with the...
Yeah, so let's do another one. Let's just do another one. Is that okay, or do you want to see this one? I'll hold this up here for a second.
Well, we can do another one. I just want an example one.
Yeah, let's do another one. Okay, so let's actually try to get... yeah, let's just do another one. Okay, so I have a container here. Here's my container. All right, and it has a certain amount of gas in it. And then I have a new container here. All right, and it has a certain amount of gas in it. And I want to know what the new volume of this second container is if I know that for this container here, and this is the same container, so I've done some squishing here, right? If this container here was at 1 liter, all right, what is the volume of this container if I've started off at 0.9 atmospheres of pressure, and now over here I'm at 1.3 atmospheres? What is the volume of that container? All right, do you want to help us out with that one, Camille? What do we got to do?
I can try.
You tell us what we should do.
Well, it's the P1 over V1 equals P2 over V2, correct?
Okay. We know that the pressure and the volume of a container will always be related. The initial pressure and the initial volume will always relate to this final pressure and the final volume. Now,
Yes.
there's some things we didn't change. There's some things we didn't change here, right? We didn't change the number of moles of gas in that process, because obviously if we somehow pumped in a bunch more gas in here, then the volume would go way up. Or if we just removed all the gas, then the volume would go way down, or the pressure, sorry, would go way up. If we removed all the moles of gas, the pressure would go way down. If we heated up this system, if we did this change, but then we also added a bunch of heat, what do you think, Brielle? What would happen if we heated up a system? Do you think that would decrease the pressure or increase the pressure?
Would it decrease it?
Well, that's a good question. Have you ever taken a can, a hairspray can, and thrown it into a fire, or like a shaving cream can and thrown it into a fire? Have you ever had that?
No, but I would expect it to explode.
All right, so what's causing it to explode? Whatever's inside? Yeah, the pressure has increased inside, right? And it tries to come out, right? I learned when I was a kid, my mom gave me the job when I was about 7 or 8 to burn the garbage. We lived on kind of a little mini farm, not really a farm, but I don't know why she didn't want to take the garbage to the end of the road, but she'd always have me go out and burn it. So I would burn the garbage in this big barrel and everything was fine, except I knew every time I took out the bathroom garbage, I didn't know why, but I knew that it would often explode, and I couldn't figure it out for a long time until I realized it was the shaving cream cans or the hairspray cans that were in there that kept exploding. So we know a little bit about that as well. If you take a container and heat it up, then the pressure changes as well. So in this scenario here, we didn't say anything about changing the number of moles of gas. We didn't say anything about changing the pressure, or sorry, the temperature, right? We have to keep a few things constant. So did you get it, Bria? No, Camille, right? Did you get it? Did you get the answer for this one? What is the new volume?
Okay, here's my question. Okay, sorry. So it'd be 0.9 over 1, and then 1.3 over don't know.
That's right.
Okay.
So we got 0.9x being equal to 1.3, right?
Yes.
Cross multiplied there. So 1.3 divided by 0.9.
I don't have my calculator with me, but I can pull it up.
All right. So 1.44. Did I do that right?
Then you have to put that.
1.3 divided by,
I got 1.17. I did.
let's see. Oh, sorry. 1.3.
Oh, wait. I did.
So 0.9 atmospheres, 1 liter. How many liters, X, it goes down here, if I now have 1.3 atmospheres? 1.3 atmospheres. Pressure, yeah, 1.3. So, did I do that wrong? 0.9x equals 0.9x equals 1.3. And then divided by 0.9, divided by 0.9, 1.3.
I got 1.4 repeating.
1.4.
I did as well.
Did I do that wrong?
What is the answer supposed to be?
Well, shouldn't the volume have decreased if our pressure increased?
Oh, yeah.
Did we do that wrong on the last one? Where's our last one? So we increase the volume. P1,
The pressure
P1.
also increased in the last one whenever we increased the volume.
What's that?
In the last problem we did, we had the pressure increasing as well as the volume was.
So this scenario here, our pressure was 2, our volume was 100. If the volume expands to 2,000, then the pressure has to go down, right? Or no, the pressure has to go up. Oh, you know what? That's not the correct formula on that slide. Sorry about that. That is not right. This is the relationship. It has to be PV equals PV. Like that. Pressure volume, like that. Because if you have the volume increase, the pressure has to go down. I didn't catch that, but that is so that's wrong on that slide there. So let's try that question again. If we have 1 liter, 0.9 atmospheres. How many liters if the atmospheres goes up to 1.3? And we have to solve it like this. P1V1 equals P2V2. All right, Brielle, or no, Camille. Camille, you want to try this one again?
Yeah, I'm writing it down right now.
Okay, pressure initial 0.9, volume 1 liter, pressure final 1.3. What is our final volume then?
So it'd be 0.69.
All right. Okay, so our final volume here is 0.69 liters. If our pressure somehow increased, our volume must have decreased. Right, very good. Well, that concerns me. I'll double check, make sure that we don't have any. We'll have to pay attention to the next slides. So that's the relationship between pressure and volume. Pressure and volume. Now let's look at our relationship between volume and temperature. Volume and temperature. Now we already talked about this a little bit in terms of our intuition. What did we say happens? Whose turn is it? I think it's Jace's turn. Jace, well, Jace, are you ready to answer questions? He kind of joined a little bit late.
Yeah, I should be good.
Okay, so give me the thumbs up on there so I can remember if I get back to you.
Okay.
If I increase temperature on a system that's fixed volume, so here it is, it's my shaving cream can that I just threw into a fire. It has a number of gas molecules inside. If I increase the temperature on this system, what do you think will happen to the pressure?
It should, that pressure should increase if you increase the temperature.
All right, the temperature should increase if I increase the pressure. That's right. So we say that temperature and pressure, volume, temperature and pressure are directly related to each other. Now, this is if we have a fixed volume, right? Whoops, sorry, fixed volume. What if we have a volume that can expand, like a balloon? What do you think will happen, Jace, if I heat this balloon in terms of its volume? How will its volume change?
The volume would probably, because it can expand, I would guess that the pressure would stay the same for a short amount of time until the balloon could no longer expand anymore, and then it would end up breaking because the pressure would become too much.
Okay, very good. So if I increase the temperature, so let's say this is 20 Kelvin and I go up to 200 Kelvin, right? If I increase the temperature, then the volume of my gas will increase if I have a variable volume. All right? If the volume is allowed to vary of the system, of the container, then our volume will increase. And in that scenario, then we see that there's an direct proportionality, right? Direct proportionality between the volume and the temperature. As the volume doubles, the temperature will double. Or sorry, as the temperature doubles, the volume will double. Very good. So let's perform a little practice problem here then. Okay, if I have a balloon that has a volume of 1 liter, and I raise and let's say the temperature here is 20 degrees Kelvin, and I raise the temperature to 30 degrees Kelvin, what will the new volume of the balloon be? All right, Bree. Oh, Bree, are you watching just for fun?
Yeah, I'm here. Just
Okay,
for fun.
wonderful. Bree is
To make
our
sure I know it too.
Bree is our tutor, right? And so if you ever have any questions and you hopefully saw the email or the announcement about the opportunity to get extra credit on this first exam, if you connect with the tutors before Tuesday next week. So that's a great opportunity. But we'll ask Camille. Camille, what do you think? What will be the new volume here of our container?
I'm working on it. One second.
Not sure?
Well, I'm working on it. I'm putting it into the V1
Oh, I
over
see.
T1.
Do you think the volume should be larger or smaller?
I'm gonna say larger.
Larger, right? So as the temperature increases, the volume should also increase. So that relationship that's shown up there, V1 over T1 equals V2 over T2, should be right. Now the other one, that relationship didn't go with the other one because the other ones were inversely proportional, but these ones are directly proportional, so that should be right there. So our initial volume, 1 liter, our initial temperature, 20 Kelvin, right, going to 30 Kelvin. So our new volume here should be larger. Did you get it, Camille? Get an answer for us there?
1.5.
1.5. X equals 1.5 liters. Okay? So there's our relationship for Charles' law. Now, I don't care if you remember the names of these laws. These are just things that you already have some experience with, and we're just trying to draw upon that experience and let you see that you can arrange whatever the variables are given to you accordingly. All right? If you perform the math and it doesn't do according to your intuition, then you just have to switch it. If you have a flexible container that can expand like a balloon, then the volume of that gas will expand when the temperature is increased. Now, one thing that's important to recognize is you have to use Kelvin. You have to use Kelvin when you're dealing with temperatures. And that's because there is this linear relationship associated with the number, Kelvin number, all the way down to absolute zero. And Sarah, I don't know, do you remember what absolute zero is, Sarah?
That's 0 degrees Kelvin.
0 degrees
Right.
Kelvin. What's happening in absolute zero? What does that mean?
I'm not sure. Is it the coldest that?
That's right.
I'm not sure.
It is the coldest. It is the coldest that anything can be at, right? And what did we?
Is it
Go ahead.
where there's no movement of particles?
That's right, because temperature is related to motion. And so when you get to absolute zero, there's no motion. So you can't get below absolute zero. All right? We can't do this calculation, or we can't use this relationship as a calculation in Celsius. We can only use it in Kelvin. And the reason is because in Celsius, it's not a linear relationship. You get to zero and then you get into the negative region, right? And so there's not a linear relationship between 0 to infinite motion. So you need to use Kelvin when you're performing, using Charles' law here, for example. In fact, in any temperature-related gas questions, you always have to have temperature at Kelvin. The volumes and the pressures, those units just have to be the same on either side of any relationship. There's some other things we have to show you about that, but those are our relationships between pressure and volume and temperature. Okay? All right.